So, welcome to the first technical session of this workshop. We are starting right on time or maybe ahead of time, and this augurs well for the conference, I guess. Our first speaker is, okay, before I say that, I should mention that the talks are for 25 minutes, and there is a 5-minute gap between two talks for the changeover and also for questions. So, speakers may please note that. So, we start with Professor Guru Rao, and he will talk to us about hydrophobic interactions. Are they directional? He's been working in this area for quite some time from the solid state and structural chemistry unit of this institute. Welcome to Professor Guru Rao.
Good morning, and I should start by thanking the organizers, Arunan and Anand Suresh, for giving me this opportunity to present some of the work which is going on in our group. It's indeed a very joyous occasion to combine two centenaries, one the 100 years of hydrogen bond and the other the 100 years of our 100th volume of our Journal of the Indian Institute of Science. Real remarkable coincidence. In the afternoon, I will tell you why even though we started in 1914, this now becomes the 100th volume. It's quite intriguing. In fact, our divisional chairman mentioned that the journal was less controversial. Certainly not. It was more controversial than the hydrogen bond, as you will realize when I talk about the history of it. In fact, it has gone through many avatars, and I will talk about it in the afternoon. In this talk, you know, our chairperson is very strict. He gives 25 minutes on the dot, so I better start the talk. The talk is about our hydrophobic interactions, directional. Now, why did I give this title? I gave this title because hydrogen bonding is directional. I think that is something which has been established over 100 years. Still, there are some controversies, how directional, why directional, and things like that, but it's more or less established by all experimental and theoreticians. For a change, they have shook hands with each other and have agreed that hydrogen bonds are directional. In fact, all non-covalent interactions established so far are all directional. In fact, it looks like a hydrogen bonding situation in the auditorium also, because there is a polarization towards the electrophilic region, the region where you can get out of the room as quickly as possible. So there is a nice polarization. So this is what happens in hydrogen bonding, and depending upon the strength of the bond, the proton starts to move from one end to the other. So it takes all shapes, all kinds of interactions. It takes electrostatic interaction, sometimes even goes very close to covalency and so on. Thanks to Pauling, who in fact told us what is what. And I think that has not changed over the years, even though there are some controversies again. What is interesting in science is to have controversies. The most controversial one, as I see now, is the hydrophobic interactions. It's very ubiquitous. In fact, it is second only to hydrogen bonds. But I noticed that this is quite controversial because we have not understood anything about it. Even though it is so prolific in biology, so prolific in chemistry, and now of late in material science, it occupies a central theme because this is something which assembles everything. And this is a force which at this moment we have to see. We'll try to answer the question. I don't think we'll answer the question today. We'll make an attempt to answer the question whether it is directional at all. Probably not. Because it's good that it is not directional, because that is the force which brings directional interactions together. And that's how hydrophobic interaction seems to gain importance. Let's see how to get to, again, the question of definition. Which is the best definition for hydrophobic interactions? I looked through literature, and now you see I'm an out-of-service professor, so there's a lot of time to look into literature, which I didn't do earlier, as I had other issues with the institute. But now I am a free bird, so I could look through literature more cautiously. There's so many definitions, some hundreds of definitions which come for hydrophobic interactions. Biologists want it one way, chemists want it the other, material scientists, I think they don't want to worry about it, but they want to believe it exists. So as a consequence, we have some kind of a controversial situation here, but I thought the best definition, interestingly, comes from the biologists, and that is what this is. Hydrophobic interaction is the attractive force that drives the aggregation of nonpolar moieties, this in aqueous medium. So whenever we talk about hydrophobic interactions, we invoke the presence of water. The moment we have water, we have interactions, obviously there is the presence of, in the background, the presence of hydrogen bond. And in that context, the issue associated with whatever issues are associated with hydrogen bonding get carried over to hydrophobic interactions. This by far I thought is a definition which is non-controversial, because it says there are nonpolar moieties and they avoid water, and as a consequence they assemble with each other, and that is defined as an attractive force. So we will see whether it is what it is, in what sense it is attractive as we go along. These are some examples which you will see in many textbooks, so I just thought I will flash it. This is oil separating from water, we say hydrophobic interactions. The little drop of water on the surface of a lotus leaf, which you find in ponds. And then of course the assembly of molecules in an aqueous medium with the polar head pointing out. And then the very important and very controversial protein folding. In all these, the hydrophobic interactions, as we see, play a key role. Now, what is the motivation for the current study which we have done? The motivation for the current study comes from the common notion that the HIs, I will make it short form, hydrophobic interactions, are mediated exclusively by water molecules, and that is a common notion. But if you see some of the recent papers, particularly involving hydrophobic interaction discussions in gas phase, you see that the existence of hydrophobic interactions in gas phase has been established by the electrospray ionization mass spectroscopy in 2009. This is the publication on that, hydrophobic protein ligand interactions preserved in the gas phase. This means to say that the presence of water is a questionable aspect as far as hydrophobic interactions are concerned. They can occur even in gas phase, they can occur in liquid phase, they can occur in solid phase. So as a result, are they directional? We come back to that same question. The second recent publication is again based on AFM studies, and these AFM studies also indicated that in the gas phase we have the strength of nonpolar surface interactions. The most important paper which came in from theoreticians, which sometimes attract the attention of the experimentalists. It's not normally the other way around, but in this particular case we found that the computational studies from theory on methane dimers, N-alkanes and polyhydrones, which appeared in Nature Chemistry, this is in fact the motivation for our work, and I will elaborate on it a little bit after I tell you something about directionality. Directionality is the key feature to describe hydrogen bonding. In fact, we describe it in terms of bond lengths and angles. The entire area of crystal engineering is stemmed out of this idea that we have this association of molecules, the aspect of polymorphism in drugs and pharmaceuticals. All these aspects depend upon the directionality, the strength and the directionality. Directionality comes from the measurement of the length and the angle. What you should remember is, nobody told us that the two atoms will decide to form a straight line between them, and that is the interaction distance. It's not necessary that the two atoms should be along a straight line. We take a scale and join it and say this is the bond length. And most often than not, spectroscopic evidences suggest that this is probably okay. But essentially, the electron density distribution in the bond makes a very interesting approach. And in fact, it makes a totally different kind of a ball game. We will expand on that, and we will see how we can use that to understand hydrophobic interactions a little more better. The other intermolecular interactions like halogen bonding, nicogen bonding, chalcogen bonding, carbon bonding, all these, the elements in the periodic table starting from 14 to 17, all these elements have these kind of non-covalent interactions, which are also highly directional. This has been established in recent times. What makes me very happy is that I did not know anything about it, but I did some work as a postdoc in JAX 1981. You see, this paper now has become a very important paper. Nobody even looked at it earlier, but suddenly in the last 5 years, when I see the database and also the Web of Science and so on and the citations, suddenly the graph has gone up like that. The reason is the fact that this is the first paper where we saw that when atoms start to interact with each other, they become non-spherical. The spherical shape, the van der Waals radius, which we associate with the atom, now is no longer a spherical entity. It becomes non-spherical. And this is the reason why the so-called sigma holes, which later developed based on this idea, and now it is very prominent, has been recommended by Pulitzer and others. So in this case, when we did this analysis in 1981, this is something which, in fact, our divisional chairman mentioned, that if you have any discoveries made in the backbench, you please quickly publish it, because it should not be too late, then you end up in the front bench. So this is something which you should realize. So if you want to publish it fast, do it fast. So this somehow went into oblivion. This work was very simple. What all I did was, at that time, very few data points are here. We found that if the sulfur and sulfur come close, less than the sum of the van der Waals radii, there are only two approach ways in which it can come. One is to come at 90 degrees, there is an accumulation of these dark dots, or come at 180 degrees, which is an accumulation of the open circles. Of course, there is a distribution because the statistics does distribute these things, but basically it tells you that electrophiles and nucleophiles look at these interactions differently from each other. And the consequence of that has been discussed there. And that leads to the fact that there is what is known as a sigma hole. Sigma hole in these molecular species essentially means that we have a directionality that is associated with the possible incoming interaction that can develop in the non-covalent nature. And that is what was established, and now it is very popular among theoreticians and experimentalists. And considerable amount of work has gone on in finding out this sigma hole. What we found over the years is that all these subtle features, these are all very, very small in terms of electron densities. These are all fractions of one electron density. These are about 0.08 electrons per angstrom cube kind of densities. And so if you want to look at that, then particularly from experiments, the observation can be done through experimental electron density from high resolution X-ray data. And this methodology to analyze this was developed in terms of the multipole model, and that was due to the work of Hansen and Coppens. The work of Bader is essentially to see the topology of interaction region, so that we can examine how these interactions are facing each other, what is the direction that is involved, what is the angle in which they come, and what is the strength of the electron density that develops between these bonding regions. So these aspects have been discussed in these by these approaches. So by far we find that it so happens that there are very few practitioners of this area in India now, but there are some around the world. And now, in fact, in 2017 in IUCR, it was decided that this area, if you say charge density, people don't look at it. If you say momentum density, there is a small group, charge density a small group, spin density another small group. So what was decided was to combine all these things and call this area as quantum crystallography, hoping that quantum crystallography makes a little more sense to the rest of the world, because anything quantum is looked at with some awe and some kind of a very special feeling from the time quantum mechanics and quantum chemistry or quantum physics or whatever developed. So we decided to call it quantum crystallography, and that name now is stuck. So this methodology which we use is referred to as quantum crystallography. So based on that, we looked at several structures, the details of which I will not go into, because I know the first 10 minutes of the time given is over, and so only I have 15 more minutes. So, what I tell you briefly is to see that in this particular case we are looking at a CHO bond, and what is plotted is here is the so-called deformation density map. The deformation density map removes the spherical atom essentially and shows what is left in the molecule after we remove the spherical atom contribution. So, if you have, let us say, a spherical carbon atom, a certain amount of the density goes from the carbon atom to the next interacting atom. In this particular case, we have looked at a CHO bond. This is the oxygen and this is the carbon and the proton, and we see that this is the deformation density map, which tells you that this hydrogen bonding is highly directional. So, we see that this is the interaction distance, and at this particular distance we see that there is a polarization of the electron density associated with the oxygen here, which essentially represents a kind of a situation similar to this. And as a consequence, we have a very weak though established CHO hydrogen bond. As we go to closer and closer or better and better hydrogen bonds, we will see that this becomes more and more linear. Spectroscopists will be very happy, hydrogen bond becomes linear as we go to stronger interactions. The same has been observed in case of the 14 to 17 periodic table elements, and one of the examples shown here is the three-dimensional, this same 2D map has been shown here as a three-dimensional deformation density map, and you see that a little red thing which is sticking out here, that is corresponding to the so-called sigma hole. And so you see that the carbon to oxygen distance is short, and that is the one which in fact generates what is known as carbon bonding. And in fact, when you look at the actual bond distance between carbon and oxygen in terms of the electron density distribution, you do what is known as a bond path drawing, and you see that the bond is now going this way. So, it is a bent one, and there is what is known as a critical point at the center of this bond, which essentially represents that the first gradient of the electron density goes to 0 at that particular point. So, whenever you have a critical point of this kind, you could generally call it a bond. It could be a strong, in case of covalent bonds, it will be fairly well described. So, essentially this tells us that the hydrogen bonding and the so-called non-covalent bonding associated with halogen, nicogen, etc., they are all directional. Right. Now, as I told you, that paper in Nature brought us the motivation to do this work, and they talked about the various intermolecular conformations a methane dimer can take. They looked at, for example, a 1:1 head-on interaction where the proton faces this proton, and in this particular case it is 1:2, the plane faces this. Then we have the 2+2 eclipsed, 2 staggered. That means if you have the methyl group like this, if it is eclipsed, they will overlap like this. If it is staggered, they will rotate by 60 degrees. And then the interaction develops, the so-called hydrophobic interaction between the methyl and the methyl group. And they calculated some of the numbers. I will not have time to go through it, but I will just tell you highlight the two things which attracted our attention. That is the 3,3 eclipsed and 3,3 staggered. We wanted to engineer molecules into these kind of situations where we have the methyl groups approaching each other. So, essentially you see when you calculate these distances from theory and then they calculated the topology that is associated with this, some of the experimental values which could be generated are given here, but basically you see that the energy that comes out is about 2, highest energy is about 2 kilojoules per mole, fairly it is somewhat subtle but not really faint. Sorry about my throat is in bad shape. That's it, thanks. So, they describe this as a weak homonuclear RH-HR dihydrogen interactions. Just notice that this is again involving a hydrogen to hydrogen contact, and they believe that it is highly directional at this stage. We looked into the database. This is the first thing all of us do nowadays. We have the plethora of data which is accumulated by X-ray diffraction. So, we look at the database and see how many interactions are possible between the two methyl groups when they approach each other. We found that if you have a staggered conformation, that means this torsion angle is 60 degrees, plus or minus 10. And this is the eclipse conformation where the phi value is 0 to 10, plus or minus 10. When we did that, the total number of hits with short ME-ME contact. So we take the van der Waals radius of carbon to be carbon to carbon van der Waals distance as 3.4 and hydrogen distance as 2.4 in terms of the van der Waals radii. Van der Waals radii being half of each of these for carbon and hydrogen. And then see what are the ones which are less than these numbers in the database. We found 3038 possible short ME-ME contacts. So the mean distance between the methyl and methyl, that is particularly between C and C, happens to be 3.32 in case of staggered configuration, which has the more number, 1840 hits, and in the eclipse configuration we have 69 hits. And in that we see that the angles are 61 here and 4.8 in agreement with these two, and then the distance of the hydrogen to hydrogen is 2.67 and 2.64. Very interesting, because the hydrogen distances are greater than the sum of the van der Waals radii, so that the hydrogens are not interacting. The so-called RHHR is questionable if crystal structures are to be believed. Okay, and these are huge number of crystal structures with lot of accuracy and done in many cases. Some of them are not so accurate as well, but essentially we have a situation where we have the carbon to carbon distance less than the sum of the van der Waals radii and the hydrogen distance greater than the sum of the van der Waals radii. That means the two carbons must be approaching each other. Then we ask the question, is it just a carbon bond? Like the carbon bond we have already seen, and so it will be directional. Let's see what happens in that kind of a situation. What is happening therefore is, we take this as a statement, we suggest that there is more to the formation of ME-ME hydrophobic interaction than just appears to the eye. It is not a dihydrogen contact. We looked at the PDB, the protein data bank, and looked at very accurate protein data, because protein data also has these kind of course, basically proteins we say are assembled through the hydrophobic interactions, the solvent water being outside and so on, the accumulation of proteins take place, the assimilation of proteins take place, the assembly occurs in such a way that we have interactions. So I gave you 4 examples here, which is high resolution data sets. You see that there is a 3.34, excuse me, 3.01, 3.32. Of course, these are not very accurate, but accurate to these resolution limits, but I think they are significant. So we have therefore from the proteins also the existence of these carbon to carbon short distances. Then we designed 4 molecules. Excuse me, throat is very bad today. We made 4 molecules, and in such a way that we have these methyl-methyl interactions put in. These are 4 co-crystals of caffeine and 3-hydroxy in this case, caffeine and 3,5 whatever, and theophylline and 2,5-difluorobenzoic acid, and tetramethylpyrazine and oxalic acid. You see there are 2 types of methyl groups here, the methyl groups which now come closer than the sum of the van der Waals radii, which are marked here, and there are other methyl groups which do not come closer than the sum of the van der Waals. So we have 2 types of methyl comparisons which we can invoke when we study these structures, and we did the multiple analysis on this one with very high resolution data sets. The crystallographic details are given here, I won't go into it. I will assure you these are very high quality data sets, okay, you believe me. Because we have data up to sin theta by lambda, as you see here, 1.08, 1.08, 1.11 and 1.11. And then the R factors and the goodness of it are all good. What is more important is the residual density is comparably very, very short, and the minus and the plus are very close to each other. That means it's a high quality data sets. 9:42, 2 minutes only, wow, I have to rush. So we did the electron density analysis, and in this we see that there is no directionality that is associated at all. We don't see any sigma hole kind of interaction, anything like that developing here. And in fact, when we look at the 3-dimensional deformation map, we see that the red tongue is pointing out, it is not really pointing out to the blue because there is an intervention of this red tongue. In all these 4 cases, it's not just that the sigma hole is pointing directly to the electron dense region. And as a consequence, there is no sigma hole kind of interaction that is seen here. So we then went and calculated the densities that are the electron density distributions. We calculated the kinetic energy and the potential energy. What it essentially done, we also looked at the bond paths. The take home lesson here is that the hydrophobic interactions are essentially group interactions. There is no directionality. So non-directionality is what is suggested here. It is different from atom-atom, it is different from sigma hole bonding like hydrogen or halogen bond. Now how do we quantify it? We did the theoretical calculations based on this. We calculated the interaction energy. It is the sum of this plus this plus this plus this. You have these numbers here. You see essentially it turns out to be that it is a dispersive type of interaction. As you see, these numbers will subtract out those numbers, which is essentially the repulsive terms. And you see this plot which tells you for the 4 different compounds, the values essentially suggest that it is purely a dispersive in nature. The interaction is purely dispersive in nature. Now if you look at these 3 molecules which are involved in our 4 crystal structures, we see that there are different kinds of methyl groups, as I mentioned. There are methyl groups which are hydrophobic interaction involved, which are shown in red, and the one in blue are shown in the I will need 2 more minutes if with the permission of the chairman. Anyway, we started early on time, so 2 more minutes is okay. Now we decided that what is the reason? See, we have the short distance, we have the interaction developing. What is the reason? We now saw it is also energy involved is dispersive energy. But what is it that is causing this to happen? So we looked at something very new. Something very new is the comparison of the atomic displacement parameters taken now from the neutron data. Of course, we couldn't get the low temperature neutron data, unfortunately. We got the room temperature neutron data. You see that in general, the thermal ellipsoids that are associated with these protons, those who do crystal structures regularly and don't believe in the fact that we can get hydrogen positions, have to worry about neutron. This is the data from neutron, so we can get the hydrogen positions accurately. And these show larger thermal vibrations compared to the other methyls which are not participating in this. So we decided to do a thermal analysis. The thermal analysis, originally a program has been written which is THMA. This was by Maverick and Trublet way back in 1987. And that will tell us how to distribute these thermal features with respect to this large thermal ellipsoids. It could be a disordered 2-atom position, or it could be a position in which the whole thing is dynamic. It could be a dynamic disorder or a static disorder. So the proton positions are, even from the nitrogen, are not very accurately located. And so I have plotted out here the values, and you see that we calculated the corresponding entropy from the method of Madsen and others. Sorry, I don't have time, otherwise I would have explained it. And we get to the energies, and we see that these now are stabilization energies. So the logic is now that the torsional rotation associated with these, something like what I will show now, something like this. So it is the methyl groups which can be both staggered as well as eclipsed in crystal structures. We isolated them. In this particular case, what is happening is these large thermal vibrations essentially represent a torsional rotation. This torsional energy, or the torsional energy generated due to torsional entropy, seems to be the base cause for bringing hydrophobic interaction. So when once this happens, the dispersion energy gets distributed in these regions, and as a consequence, we get a short contact between carbon and carbon. And that seems to be the result, and of course I will skip this, otherwise my chairman will throw me out. So this is essentially to tell you that we did a very careful analysis of the X-ray data as well, because we wanted to look at whether it is a realistic effect or it is just a temperature effect. So we did the variable temperature XRD, and then use the quantum crystallographic approach of what is known as the Hirschfeld refinement, atom refinement. I wanted to give you some detail, but there is lack of time. But we use the Hirschfeld atom refinement to tell you that even though the temperature brings it down, you see the arrow marks, those are the active methyl groups which are participating in the hydrophobic interactions. They appear to have larger energy that is associated with the torsional entropy. So the net effect appears, it has also been verified by C13 NMR studies done with the help of Ramanathan and his co-workers. And you see here that if you look at C12, the C12 is essentially now shifting to the higher fields. It is the characteristic upfield shift is essentially due to, you see C10 does not shift, C14 does not shift, C12 shifts. And that seems to be supporting the fact that the two carbon atoms are coming closer than what was anticipated. And this brings to the last slide. So in conclusion, we can say that the dispersion interaction is the dominant interaction between the two methyl groups. And when two methyl groups come too close to each other, the torsional entropy takes over. And because of the torsional entropy, we have this interaction that is developed. And this now we say that therefore the bond paths reveals it's a group-group interaction. So there is no directionality that is associated with the hydrophobic interaction as we see as of today. It can keep changing. This work has been published in JPC Letters about a month ago. It keeps changing, and of course this is something which the colleagues here should look into. Pinak is sitting here, so he is someone who is really interested in to see into what happens to biology if we have this kind of interaction. So thanks to all the work which I have presented here is done by this red marked fellow, Saunak Sarkar, who is now a postdoc somewhere. He is in Denmark, Aarhus. And then Sajesh, he did a part of this work. Alison Edwards, thanks to her for getting us the neutron data. Ramanathan for the NMR data. And of course, J.C. Bose Fellowship, which just ended. So I'm now, out of service professor. And the last but not the least is I would like to dedicate this talk to the memory of Professor K. Venkatesan, who is my mentor. He was a professor at IISc for the younger audience here. He started crystallography along with Professor Manohar in IPC in the departments of chemistry. Until then, crystallography belonged only to physicists. In fact, I am also a physics trained person over the years. I turned to become a chemist. I don't know what chemistry I know. Arunan will vouch for it, but anyway, that's what life goes on. And in this particular case, he passed away 3 hours before 2020 ushered in. And that is, so effectively, he died in the last part of 2009. So I dedicate this talk to his memory. And thank you very much, and thanks for your patience. Still have 1 minute for question, 1 or 2 minutes.
You said when two methyl groups come together, the CC distance is less than the van der Waals radii, but HH distance is more than van der Waals radii. So what will happen if this is the normal tetrahedral carbon atom? This will be something, it will be stretched like this. Mm-hmm. That may change the HCH distance. Did you look at that, or yes. It is?
This is clear from the entropy calculations, because what we are doing in the entropy calculation is to take this and see this rotation. This is the torsional rotation, right? So when we do this rotation, that also implies pushing away the hydrogens. For example, if you have these, let's take the eclipse configuration, and then we do this. When we do this, the proton positions, they move away from each other, either in the staggered position or in the eclipse position. So from the crystal analysis point of view, crystal structure analysis point of view, and also from the values of the ADPs we have and the distribution of the positions of the atoms in the dynamic situation, you see that the distance between the hydrogen and hydrogen will increase between the standard staggered and the standard eclipsed configuration. And therefore, the orientation is only in a planar. I agree that it's a possibility that they go away like that. The possibility of that going away would have been seen in our bond path analysis. But we do see bond path analysis tells us the hydrogen-hydrogen CH is also there, or the critical point is also there between them. And therefore, it's a question of, if you believe in the presence of critical points, the aim analysis, then it is a possibility that it can happen. So it looks like the torsion entropy seems to be the dominant.
So unfortunately, in the interest of time, we have to cut short. This is exciting. I'm including Professor Arnan. I'm going to cut short. So we'll go ahead with the next speaker. Please join me in thanking Professor Gurrao for the exciting talk.